This is Chapter 8, Deformation and Metamorphism, Lecture 2. In our last lecture, we left off on foliation in metamorphic rocks, and we'll pick up with lineation. So lineation refers to linear features, like deformed pebbles and the like, in metamorphic rocks. Lineation can be expressed by oriented minerals. In this case, we have these long blue crystals that are in a preferred linear orientation. You could also see lineation in terms of stretched crystals. That's where these long axes of feldspar crystals are stretched out in a horizontal direction. Or with shearing marks, these minerals were actually smeared out during metamorphism. So these are linear features. Other metamorphic features can include preserved features such as ripples. If the rock isn't too deformed, we can still see pre-existing features, like from a sedimentary rock. You can have a shear zone. Those are zones within which rocks are more sheared than rocks outside the zone. So there's a lot that happen here. Within the shear zone itself, it's going to be different than the surrounding rocks. Folded pebbles. We have, in this case, a former conglomerate. Conglomerate pebbles were flattened during metamorphism and deformation. We can have deformed foliation. That's where cleavage and foliation were later deformed by folding. In this case, gneissic foliation folded during a second metamorphic event. And as we look at these metamorphic rocks, I want you to keep in mind that all of these rocks started out as a different type of rock. Like this used to be just a sedimentary rock, a conglomerate. That's called its protolith, the rock it was originally, and then it became something different after it was deformed or metamorphosed. So, thinking about that, metamorphism of sedimentary rocks, that's a good transition. So, shale is a sedimentary rock. It can experience different grades of metamorphism. Shale is the protolith, the first rock that wasn't metamorphosed. But under stress, at low grades, shale can become slate, a metamorphic rock once used for chalkboards. I don't know how much it's used for chalkboards anymore, if we even use them, but it used to be used a lot. More metamorphism, higher grades of metamorphism, we get something called schist. So you go from shale to slate to schist. At even higher grades than that, we get gneiss. So it looks quite different from the protolith. All right. If you metamorphose sandstone, it will become something called quartzite. Limestone can be metamorphosed to marble. So protolith of marble is limestone, or dolomite, or dolostone. Okay. So metamorphism of igneous rocks. If we start off with basalt or andesite as our protolith and we metamorphose those, we can get greenstone. This one is actually from Marquette, Michigan. Or green schist. Granite can metamorphose to gneiss. Various rocks end up being gneiss. It looks a little different, sure, based on the protolith, but it's classified kind of the same in terms of what sort of metamorphic rock it is. And we see this gneissic foliation here. Okay, so what are the causes of metamorphism? Well, you need pressure. Higher pressures can compress rocks and cause some minerals to be unstable and others to be stable. Temperature, an increase in temperature weakens rocks and causes new minerals to grow. Or tectonic stress, that can cause rocks to move and deform internally. An introduction of fluids can interact chemically with certain minerals and cause new minerals to replace existing ones. So the response of the rock would be to deform and or grow larger minerals, grow new minerals, or be cut by veins like from these fluids precipitating new minerals. And there's two basic types of metamorphism. First off, contact metamorphism. Heating near contacts of igneous intrusions would result in contact metamorphism. And then there's regional metamorphism. That's going to be a larger area typically. We have burial, heating, and stress resulting in regional metamorphism across a large area of rock. So what are the causes of regional metamorphism? First, we can have burial. If rocks are buried, they can be taken to higher pressure, temperature conditions. You could have rocks buried by sedimentary or volcanic burial, or buried due to, say, a hanging wall from tectonic force moving over them. You could have subduction as well. Rocks move downward in subduction zones like so. Or you could have heating. So heating can happen through the introduction of magma into an area. It would impact the rocks around it. You can also have crustal heating if there's some sort of flux or flare up from deep within the earth. That can impact rocks as well. Let's see. You can also have hot fluids introduced. Those would carry dissolved chemicals and they can hydrothermally alter the rocks. Any kind of change in stress can have an impact as well. Tectonics can cause rocks to deform and result in new metamorphic fabrics. These are not pictured, but you could have like shearing as well. One rock mass moves past another to deform rocks close to the zone of shearing. Or something like shock metamorphism, where meteoroids could strike the earth and send shock waves through rocks. Okay. So there are chemical processes during metamorphism. We'll start off with recrystallization. Existing minerals can recrystallize or new minerals can grow during metamorphism. You could have pressure solution. Material is dissolved from highly stressed edges of grains as such, and it precipitates out elsewhere in the rock, and then the rock will lose volume under pressure solution situation. You can have remobilization. That's where chemical constituents in the rocks diffuse, dissolve, or partially melt, and that's going to produce light and dark bands in a rock like gneiss. All right, so those were chemical processes. Let's look at physical processes. You can have deformation of objects. That can flatten grains into pancake shapes or long, thin shapes. You can have rotation. So elongated and platy minerals can rotate so they become almost parallel to one another. You can have shearing, which aligns or stretches out previously unoriented crystals. You can also have like small scale folding. If layered rocks are compressed, they generally will fold. Or you could just have fracturing, where parts of rocks can fracture before or during metamorphism. And another one of these charts. This will show us how metamorphic conditions vary with depth within the Earth. So we have colors showing us where different metamorphic equivalents of shale will form. So shale is our protolith, and this is all the things that shale can be under an increasing pressure and increasing temperature. Down here is all theoretical. These conditions are not found in nature. So under low pressure, low temperature, there's not going to be any change in the shale. But with an increase in both of those things, we get slate, and then something called phyllite, and then schist, and then gneiss. You go far enough into all this, you'll have melting, and you can have something called a migmatite resulting from those conditions at high temperature as well as high pressure. So this is somewhat predictable, and we'll review that. Heating by magma contact could result in, say, low pressure but high temperature. But these would be kind of typical of regional metamorphism. This situation would be something we might find in a subduction zone. So we'll look at the settings of metamorphism associated with subduction zones, with metamorphism shown in purple. All right. So we have a huge thrust fault forming as this subducted slab is under thrust beneath an overriding plate. Subduction is a relatively fast process, so the metamorphism will occur under high pressure, low temperature conditions. So we expect rock cleavage, folding, and shearing. Near this magma, the crust is heated, causing contact metamorphism, which is going to be a high temperature, low pressure metamorphic condition. And we expect little deformation in this setting. And then we get a fold and thrust belt forming on the landward side of the main belt of magma, and that's going to be associated with regional metamorphism. So metamorphism all in these areas. Low pressure but high temperature is always going to imply magmatic heat in this situation. All right, we'll look at the same thing but along a continental collision like the Himalayas. So once again, metamorphism is shown in purple like so. We have a huge thrust fault forming as one continent is thrust beneath another. And then metamorphism in collisions is mostly due to shearing and burial by these thrust sheets. Temperature increase here can cause melting of crustal rocks at depth. So we see metamorphism all along these thrust faults. And there will be some rock cleavage and shear zones associated with that as well. All right, so metamorphism at divergent boundaries, such as a continental rift. All right, so as these plates move apart, normal faults that dip inward downdrop the floor of a central rift to form a graben. So we have that here. This is a graben. Tension allows magma to open the joints and other fractures, forming dikes and fissures that are parallel to the axis of the rift. And then hot rocks beneath the rift heat seawater, which alters or metamorphoses the volcanic rocks and sediment. So we have as well, these faults forming where the two continental plates spread apart and form that central graben. The faults stretch and thin the crust. And of course, tension allows magma to rise along the faults. and metamorphism happens near the magma. All right. With a passive margin, metamorphism occurs close to the rift, but dies out as rocks are transported away from the ridge. And some metamorphism from burial of rocks will happen beneath thick sedimentary sequences on the continental shelf, but not much deformation. Again, with each of these three situations, you're going to see metamorphism in purple. I'll just circle it in case it's hard to see. All right. Strike slip faults and shear zones. We have shear stress applied. Horizontal shear stress acts to shear the two sides of a block in opposite directions. And then shearing moves rocks horizontally past one another or sideways. Shearing in the upper crust of the earth occurs along faults, but at greater depths, shearing will occur along a shear zone. And then shear within plates can offset rocks, say, hundreds of kilometers or less than a meter. We can get something called drag folds associated with that. Transform faults are strike slip faults that accommodate the lateral displacement to one plate past one another. Okay. So we have an active fault here offsetting stream channels. That's the type of displacement we would expect associated with a strike slip fault. All right, folds related to faults. So here we have a reverse fault. A fault forms in crystalline rocks and propagates upward through the crust. Sedimentary layers on crystalline rocks fold in advance of the rock. So there you have like a monocline forming. You can also have a fold related to changes in fault dip. So a fault slices through layered rock. It cuts along weak rocks before continuing upwards. And as the layered rocks are pushed up the fault, they are folded. They're forced to kind of conform to the bend in the underlying fault. And we see that here associated with the thrust fault. All right, so there's another thing called fold and thrust belts, because folds and thrust belts occur together in, say, regional belts, like the Rocky Mountain Front in North America. So this is an idealized example of that. That's where we have thrust faults, those sort of shuffle rock layers. They displace older rocks that are in gray or blue on the bottom over the younger rocks, which are on the top. We'll have folds related to those faults. Those other folds develop away from faults due to overall shortening. And you can have cleavage and folds caused by shortening as well, and the cleavage is in this direction. Most of those thrust belts contain variably developed cleavage, like it won't be uniform, and it's related to folds and shear along the thrusts. Here's an example of a fold and thrust belt. We can kind of see the folding here. That's in Argentina. And on the right, we have anticlines and synclines formed by shortening in Arizona. We'll look at how rock cleavage relates to folds. So cleavage can form vertically, as shown here, horizontally, or somewhere in between. Keep in mind that cleavage will be perpendicular to bedding in the hinge of a fold. So you might have to look back at those previous slides to kind of understand that. I don't know how well you can see it, but we have dashed lines showing how this fold would actually look if you continue it outside of this block diagram. All right, so let's see. cleavage is at a lower angle, or it can even be parallel to the bedding in the limbs of a fold. These photographs show cleavage that is parallel to the axial surface of folds. If you like, you can fill in cleavage and beds on this hill. So we're kind of like connecting this fold. I would kind of move it through here as well, down to a limb. And we could expect cleavage to kind of go through here as such and change a little bit down the limb of a fold, because cleavage can go to a lower angle or start to become parallel to bedding in the limbs of the fold. All right, back to joints. We'll look at joints in the landscape, starting with vertical joints. These vertical joints cut across sandstone. This is from Zion National Park in Utah. We can have joint sets. Joints generally do occur in sets, which can cut layers into a series of rectangular blocks. This is in Tasmania. This almost looks man-made, but it's not. Or we can have these columnar joints with cooling and contracting of solidified igneous rocks. Okay, so these are some features located along fault zones. The first being fault breccia. So within a fault zone, you can have intense fracturing and shattering, and that creates breccia. You could also have scratch marks on the surface of a fault plane. The fault surfaces can be smooth and polished and have linear scratch marks that form parallel to slip. So that helps us determine the direction that a fault slipped. Or you can have fault scarp, and that's where fault movement forms a step in the landscape. And these can happen right after earthquakes. So geologists can go out and measure the fault scarp in a landscape. That's in Idaho. We'll also look at tilted and folded layers in the landscape. We have dipping to vertical beds here. The layers are sort of dipping this way, but they form nearly vertical fins near the base. So they're dipping parallel to the slope at the top, but then they change with that folding. Here we have dip slope. With erosion, weak layers can rapidly strip off a rock outcrop. They'll slow though when encountering hard layers, forming a dip slope parallel to the layers, and this is in Utah. Or you can get something called a hogback. So you have erosion of dipping layers on a tilted fault block or the limb of a fold, and this is in Colorado. All right, so just metamorphic rocks in the landscape here. Now they can be shiny. So this is shiny folded schist because we have a bunch of mica minerals in a similar orientation exhibiting schistosity, reflecting light. So that's a type of foliation. You could have something like this folded chert. Metamorphic rocks have many different expressions in a landscape based on their composition and geologic history. Or you could have contorted and foliated metamorphic rocks. Like I'm going to trace this folded dike. There's some vertical foliation and kind of a jagged appearance here. The point is a lot happened to that unit of rocks under metamorphism. So what are some ways we could study these geologic structures? Well, geologists look for evidence we could start off looking at this by recording observations and sketching rock relationships like displacement, linear features, potential foliation. We'd be looking for evidence such as fractured and shattered rocks near a fault zone, and this is a fault zone. We could measure the orientation of features, including bedding, folds, scratches on the fault surfaces, etc. And we could map rocks and structures, plot locations of observations, descriptions, and measurements, and collect samples. And that helps summarize this area and basically sequence what might have happened here over time throughout geologic history. So it's not just one thing. We'll look at this pretty complex looking geologic map of New England. I had the privilege of doing field camp in southern Maine, so some of these features, these orientations are familiar to me. But these thick lines are faults, these black lines. We have metamorphic rocks shown with stippling as such. Our oldest rocks are like Precambrian. Those are brown, olive green in color. Bit younger would be Paleozoic, denoted in pink, purple, and blue. And then Mesozoic, even younger, blue, green, and orange. Okay. So this is a cross section across New England. It's drawn from west to east across the central part of the map that you just looked at. So the Taconic Mountains, those are folds and thrusts within Paleozoic sedimentary rocks. So we have like a tectonic thrust sheet here. And we have the Green Mountains next. Those contain deformed and metamorphosed Precambrian rocks. And the degree to which the rocks have been metamorphosed, of course, is going to vary. The eastern part contains thrust faults that have been folded and large domes that contain high-grade metamorphic rocks. So this will show you different grades of metamorphism across New England in terms of metamorphic zones. We have low grade in this color, kind of orange here. Medium grade in like a brown color, I'd say. Tracing it here. High grade in gray. And then very high grade across Maine here, Massachusetts, Connecticut, a little bit in New Hampshire, in red. So, side note, I was able to look at rocks in a low grade metamorphic zone and map those. All right. So, the metamorphic conditions are most intense in the center of the area in red, and then they're decreased towards the west and the east. You can go back and compare this to the geologic map. So, we have this diagram to summarize the temperature and pressure history from geologic studies of central New England. The gray lines are your boundaries between minerals, separating metamorphic conditions. So the rocks in eastern Vermont were buried probably by thrust sheets, okay, as such. And the rocks in New Hampshire were heated and then buried. So you have increasing depth here, buried. And in New Hampshire, you have heating affecting those, and then burial as well. So the rocks look different based on a variety of temperature and pressure conditions. And we'll stop there for this chapter.